We're very happy to have Nico Formanek giving our next talk in the PCFS seminar series. Nico is a research scientist and head of the Department of Philosophy of Computational Sciences at Stuttgart. Research interests in the ethics of computer-intensive models, philosophy of computer-based physics, and the promises and limits of digital technologies. Today, Nico will be telling us about the epistemology of approximations in computer-intensive science. Nico, I'll pass it to you and just tell me when to click ahead.
Okay, yeah. Thanks, Andrew, and thanks for having me here today. So I will give a introduction to approximation in computer-intensive science, and hopefully convince you that they are also philosophically interesting, and there's some epistemological import in them. But before I start, so I'm actually not in a philosophy department in the university. Our institute is the High Performance Computing Center. So our institute runs one of these computing systems where lots of these approximations are used daily, right? So just to give you an idea of this background. Okay. Yeah, maybe Andrew, you can just do the next slide. So the next slide starts with a question, namely, can you compute, for example, the square root of 2 without using your phone? Do you have any idea how to do that? Maybe because we are so not so many people here, you can just if you have an idea how to do that, or maybe you already know how to do that, have learned it in school or something, you can just tell me. I'm sure Florian knows how to do it anyhow. So I'll just tell you, because I mean, once I was a physicist, and physicists do everything in the linear approximation, right? So they basically do a Taylor series, and I'll show you that. That's the first thing that would have come to my mind. But of course, there are much better ways to compute the square root function. Anyway, you can just do the next. Yeah. So the Taylor series expansion is also sometimes known as linearization. If you skip all the higher orders in numerical mathematics, it's also called perturbation theory, because it relies on the fact that you perturb the value which you want to calculate by a small quantity, and then do the linear or whatever approximation in that value. So here I just put the first few terms of this Taylor series expansions for the square root, and we can check. So actually, there's something you actually could do on a piece of paper, right? I mean, if you had the knowledge of this Taylor series stuff, which you learn perhaps in, I mean, every physicist learns that. Then you can calculate a couple of digits in the square root of 2. So I did it here for the first 5 digits. And then I checked, compared it to the true result from Google, right? So let's just assume that Google gives us the true result here for the square root of 2. And actually, this Taylor series expansion is not so bad, right? So I make a mistake of about 1.6% here. So this is already something, but of course there's more to approximation than just getting into the 1.6% range to the Google value. So there's also, you might be interested in how long does it actually take me, and are there approximations that can do it, for example, faster than what I have done here. And of course there are approximations of that kind, right? So this Taylor series expansion, it's in computational terms, it's not very good. Okay. Yeah, so we actually can do some approximations by hand, and this is how it has been done in the past, up until the first mechanical computation devices were invented, and then the electrical computation devices. It has been done like this. There was I mean, people tend to forget this nowadays, but in the past, people invested huge amounts of time in doing these approximations and in increasing their accuracy. So just to give you an idea, I have the next slide. in the heroic age of computing, which didn't involve electrical computers, it involved human computers. People were interested in predictions of Newtonian mechanics, and the famous astronomer Clairaut here is quoted with describing his efforts on calculating the orbit of Halley's comet. So at that time, that was one could say a research program in Newtonian physics to generate predictions when this comet would show up again. And Clairaut and his collaborators, they did this computation in 1757, and the comet returned to his closest point to Earth like 2 years later. And it turned out the error was 33 days. So that was actually pretty good, considering the computations they have done. And I'll just read this quote for you because it's, I think, very impressive and shows how much time people invested in approximations. So Clairaut says, during 6 months, we calculated from morning till night, sometimes even at meals, the consequence of which was that I contracted an illness which changed my constitution during the remainder of my life. The assistance of Madame Lepaute was such that without her, we never should have dared to undertake the enormous labor which was necessary to calculate the distance of each of the 2 planets, Jupiter and Saturn, from the comet, separately for every degree, for 150 years. So basically, they took the past data and extrapolated that into the future. So they started 150 years before 1759, and then did the extrapolation, and their error was 33 days. So it's actually, I think it's quite impressive. That's a fascinating piece of history in physics and astronomy, I think. And of course, all these methods for computing such approximations, they have been incredibly so they have been improved to an incredible amount. So today we can solve these problems on computers to like with much more perturbing elements, with much more planets into 1,000 years into the future. Okay, good. So we can go to the next slide. So luckily nowadays we have these computers here. I showed the computer we have at our institution. It's called Hawk. It has a peak power, if that means anything to you. So a peak computing power of 25 petaflops. So the flop is the floating point operations per second it can do. It's just like the general measure of computing power that people use to rank these systems. Of course, there are lots of caveats you have to do with. I mean, you can optimize all these systems. They have a certain architecture which is optimized to certain numerical problems. But what you can see on the right is in this measure of flops, a ranking which is done like every 6 months, I think. So this is the last one. It's called Top 500. So they have this website, top500.org, where you can go and check out all these high performance computing systems in the world, and they do lots of nice statistics there. And what you see here is like the increase in computing power. The sum of all the systems, the highest ranking system at the time point, and like the lowest ranking system, and you can see that they basically increase in a somewhat exponential fashion, one could say, although this increase levels off a bit, maybe starting around 2015, right? And this is basically one indicator of the famous or infamous Moore's law. So that I mean, Moore's law basically says that the transistors on the die, they double every I don't know 24 months or so, and you can see a similar thing here in the installed computing power in these high performance computing systems, and that is generally to be taken like as a proxy measurement for the increase also in customer computing power. Anyhow, so from this large increase, so basically that's a logarithmic scale, right? So you get a magnitude higher if you go from one teraflop to 10 teraflops, then you 100 teraflops, and you're already in the petaflop range. So this would tell us, well, basically, we can improve our approximative methods by just relying on sheer compute, on sheer power of computation. And I hope, I mean, I will discuss this a bit in more detail, what this actually means, and if we can realistically have such a hope. So I won't talk much about this Moore's law and how it could end. I mean, there are lots of engineering and physics challenges to keep that running, but so far the industry has done a tremendous job in keeping up. So I'm more interested in what does this actually mean from the point of view of the approximations of the actual algorithms. Okay, we can go to the next slide. So, of course, not all is golden, and I really like this quote by Alan Sokal in his lecture on one of the very popular and often employed numerical methods called Monte Carlo. And so he has this lecture notes where he just right away says, well, Monte Carlo is a very bad method. You should not use it. And numerical methods in general are dangerous. And so if you can avoid using them, you should avoid using them. And even in the hierarchy of numerical methods, use anything you can, don't use Monte Carlo. And then he goes on and explains what Monte Carlo is and gives like, yeah, lots of examples where Monte Carlo is actually used. So one could wonder, why do we use this method if it's so bad? And I hope I will shed some light on that later too. Okay. So much for the introduction. We can go to the next slide. So as I already said, this Moore's law, or this increase in computing power, this seems to suggest that we can, in a way, naively reduce these errors, right? So this picture I have here, that's actually quite fascinating. It's from a study of one of the numerical methods that have come to that have become somewhat a hype in the past 10 years, namely neural networks. So they look at large language models and they they just measure certain scaling laws. So they call them neural scaling laws. But what you can see here is that the test loss, which is an error, right? The error you make with your neural net in a certain task, which is not specified here, that goes down with the more compute you put in, the smaller your error is. So it suggests that actually there's some kind of inverse function of compute. So here they didn't use that much compute because compute in the petaflop days is very expensive, right? So if you compare that, our system, it has an installed peak power of 25 petaflops. So their graph levels off here a bit and is extrapolated around the petaflop range. But they did like lots of studies with these are all these blue graphs that lead into the black graph with lesser computing power. And I think it's pretty clear that the more compute you put in, the better your error gets, the smaller your error is. And I mean, for the large language models, this is fascinating in itself because it's a test loss, or not the training loss. I mean, for the training loss, it would have been expected, but there's nothing I will talk about this in this talk. So in general, I think the idea here is the more compute we have, the finer we can do our discretization mesh, the more time steps we can just do in the same compute time. And I'll just call this naive scaling, yeah, because it's in a sense it's naive. We don't have to improve on the numerical method, on the approximation. We just improve on our computing hardware. Okay. So sometimes this is, of course, not the only thing one can do, and sometimes it's we actually need some more brain power. to arrive at results. And for this, I have an example in my next slide. So this is actually a very interesting picture from a lattice QCD study where people separated the contributions to the simulation time from computers alone, so from improvement in the compute power and from improvement in the algorithm. So something you don't see very often, certainly not in the machine learning context, but of course in other fields of study, especially lattice QCD, which employs Monte Carlo methods to a heavy degree. This has been done, and I think it's very interesting because here you can see that you can actually do you can have large improvements by improving your approximation method. Yeah, you see that's like orders of magnitude here. And yeah, what is shown here is just the time, the real time. It says there the time you need for computing something over the year. So in for example, in 1959, you would have needed, like, I don't know, 100 years to compute a certain lattice QCD configuration to a certain at a certain error level, while in the year 2010 you can do it in like 10 years of computing time. Yeah, 10 petaflop years. Okay, so and this of course leads to the question, what actually do we need to do to improve these approximations, right? And to improve these approximations, we need to understand what they do. And as I will argue, we need something called error control, which I'll explain hopefully in the remainder of this talk, what is meant by this term. Okay, we can go to the next slide. Yeah, so I was talking a lot about errors, a bit vaguely perhaps. So I'll just give like a distinction that is often made in the literature between like different types or kinds of errors. One type is the computational error, and one type is the modeling error. And so it is usually assumed that computational errors are known and easily quantified, while modeling errors are not, and they are hard to quantify. So I'll have two examples if you just press the button, Andrew. Yeah. So for the computational error, you can think about this question of how many digits of pi do you actually need to calculate the moon to a set accuracy of 10 meters. Yeah? So I say this is the amount of accuracy you need, and then you can ask yourself, how many digits in pi do I need to calculate that? And it's actually quite easy to figure out how many digits of pi you need. Yeah. So it's like 5. So you can do a very rough back of the envelope calculation to figure that out. But if you want to, for example, know, so that would be a computational error, right? Error in computing pi and how that affects your overall orbit. But if you want to know what is the error that you have made by assuming that the moon is a point mass in Newtonian mechanics, well, that's really harder to quantify, right? I mean, you would have to do some kind of rigid body model of the moon, and yeah, I mean, this has been done, right? And people have figured out, well, actually, the moon probably has some kind of a fluid core by doing that, but it is really a hard calculation. So certainly not a back of the envelope type of calculation. This is why people tend to think that computational errors are easy to figure out, easy to quantify, and modeling errors not so much. So this you should maybe keep on the back of your minds. I try to cast some doubt on this assumption that computational errors are in all cases easily to be quantified and well known. But I'll do this later by giving a case example. Okay, so I'll just talk in the next slide about the sources of error. So computational errors tend to come from using in a general sense, the natural numbers instead of the real numbers. You do some discretization. Basically, in the computer, this means floating point arithmetic. There's some rounding involved, but also computational errors don't have to involve a discretizing. Yeah, you can make a computational error by using real numbers instead of natural numbers. In the computing context, that doesn't happen so much. But think about in physics, if you do statistical mechanics, then you replace sums with integrals. So you approximate a discrete quantity with a continuous quantity, and of course there are then errors involved in that too. So, but this is just some maybe some interesting case in if you use computers, you always have the problem that you reduce real numbers to natural numbers and thereby introduce errors. So this is the main source of computational error. Okay, so then I'll just, in the next slide, I'll talk about modeling errors. So what are modeling errors? Well, they have to do with your physical or whatever model you have or theory. So some examples that just came to my mind where if you use, for example, the ideal gas law instead of using the van der Waals gas law, right? Then you already know that certain gases have to be described by the van der Waals gas law, and you will get an error if you use the ideal gas law. Or also if you in Newtonian mechanics use two bodies to calculate your orbits instead of three or more. Yeah, famous three-body problem. And already there's maybe you see why we need approximations, because there's no analytical solution here for the three-body problem. And what I put here too as a modeling error is measurement error. This is in numerical context sometimes done, that measurement error. So if you have an experiment which you want to compare to some kind of computation, a computer simulation or whatever, then this is thought of as the same epistemic footing as a modeling error, somehow can be absorbed into the modeling error. Okay, so then we go to the next slide. Yeah, now that we convinced ourselves that we make lots of errors by doing approximations and modeling, we somehow have to live with them, right? And so just quoting from a nice tome on numerical methods here is the idea that, well, you can somehow connect the modeling error and the computational error and derive a rule from that when you compare them, when you have reduced them to a satisfactory amount. And in this book, it's done in a bit opaque way, because they say, well, if we have solved this numerical problem, which is here depicted as phi hat, so let's say we have a solution for that, and we have solved a replacement problem. The original problem is normally called phi. That would be and then maybe the continuous problem, some kind of differential equation you want to solve. If we can disturb that a bit in the inputs, so this delta x is like a perturbation in the input to this original problem, and if then these two problems are equivalent in a certain metric, you can somehow compare them, and you would say, well, these are similar to a degree that I find okay. Then you can say our numerical solution, this y hat, is satisfactory. So basically, this means, so if you translate that to our language of errors, that computational errors are acceptable if they are at the same order of magnitude as the modeling errors. And normally, these modeling errors, they come logically before the computational errors, at least in most contexts. So the suggestion is here that you somehow get a level of modeling error that you deem acceptable, and then try to fit your computational error to the level of modeling error. Okay, good. So we go to the next slide, yes. And this then suggests a certain kind of pragmatics of error improvement, right? So I think it's quite obvious that you should improve the biggest error first. So whatever your source of errors are, it doesn't make sense to start improving in the errors that are already small. You need to try to get them on a similar level, and to do that, you need to somehow fiddle around with the error that has the largest absolute magnitude. And improving an error, of course, means doing something to make it smaller, to reduce it. And this is what I term error control. Yeah, so you have error control if you can actually do something to make an error that you want to make smaller, actually smaller. And this error control can now come in different types. Yeah, you can have error control over your modeling error. So sometimes this just means you have to come up with a new model or new theory. In computation, it is often thought that, well, you just improve on compute. Okay, so we go to the next slide. And I also want to suggest perhaps that the quality of your approximation, the quality of your numerics, that is determined by the level of control you have for the error. So just assume for the sake of argument that all the errors that you want to control for that, they are controlled. So you have some way of turning the knobs and reducing them. And then, of course, you are bottlenecked by the error that you can control the least. So this immediately then tells you, and if that's a property of your method, which is often the case in computational methods, then this least controlled for error determines the quality of your computational method. Okay, next slide, please. I'll come now to my case study, case example, and here I actually wanted to show you this very simple and perhaps a bit naive Monte Carlo estimation of pi. So in general, if you're not familiar with Monte-Carlos, it's just a numerical approximation methods which relies on random sampling. So it introduces element of randomness, if you will, to generate estimates. And you can use that to calculate high dimensional integrals. This is, for example, why it's used in lattice quantum chromodynamics a lot, because they have the problems of having very high dimensional integrals, and all the other numerical methods that Sokal would have preferred, they just don't work, because they require so much computing power that this cannot be had in the universe. And what I meant to show you here is just that we can calculate an approximation to pi using Monte Carlo. That's actually very simple. So you just you just have to notice that the area of a circle, and so if you have a circle with a radius 1 and a square with a radius 1, and if you divide these two, then this will give you exactly pi. And then the Monte Carlo basically is you start randomly scattering points on the square where the circle is inscribed, and then you just have a rule to decide if the point is within the square or not. And then you have some kind of proxy for the areas. You can just count the points that are within and the points that are without the circle, which should be, if your sampling is done properly random, then this should be proportional to the areas of the circle and the area outside of the circle. And then you can just do the ratio of the points inside and outside, and this will give you an approximation to pi. It's a very bad approximation. It converges very slowly. This is what I would have wished to show you, but Yeah, I'll just put this Jupyter notebook with the animation. Maybe it can be attached to this video later. Okay, so this is just a very, very short introduction what Monte Carlos are. So for illustrative purposes, I wanted to give a very simple, almost naive example of a Monte Carlo method. And what this Monte Carlo method I implemented here in a Python notebook does is it approximates pi in a very bad way, one could say, but it actually harnesses the power of random numbers to approximate pi. So it's different than other deterministic methods for approximating pi. So what does it do? Well, you see here we have this half circle inscribed into this window with the radius 1, and it basically just counts the points that fall within this circle and counts the points that fall outside of this circle. Now, this is very easy to implement, and these points are randomly generated. And then we have like the number of points in one go, which are inside the circle, and in one step, which are outside the circle. Then we can do a division, like it's done here in the code, multiply it by 4, and we get a value, an estimate for pi. Yeah, the random number generation is also very simple. It just uses the regular Python random number generation method, generates the x and the y coordinate by that, then calculates the radius, and then just checks here in this if-else clause if this number we generated, this coordinate we generated, if the radius is less or equal than 1, or if it's above, so if it's inside or outside the circle. Yeah, then there's some plotting going on, but we can just let this run and see how it looks. So basically we do a plot after each point or every new point is generated. So we will see the points going up. It's counted here in this n number, and we will see our approximation for pi here. And yeah, as you might imagine, the convergence is not very fast. It's not very good. You also see that the randomness makes it fluctuate. So it sometimes gets closer to the true value of pi. Sometimes it gets a bit off. But yeah, the properties of statistics should guarantee, at least for this very simple Monte Carlo algorithm, that in the long run, it gets better and better. But you can already see it slows down here. Yeah, it's quite far away from the true value of pi, and I let this run without the animation lagging everything up. So you would need about maybe 10,000 steps to get a sensible approximation here. Really sometimes depends on luck of your random method. So as you can see, this is already affected by a problem that all Monte Carlo methods have, namely that convergence can be very bad, and this is why Sokal in his lecture on Monte Carlo said that actually they only should be used as some kind of last resort method. And now we will talk a bit about how error control actually, how errors arise in Monte Carlos, and then how error control is done there. So in Monte Carlos being like a computational method, you have the usual computational errors, right? You have rounding, discretization, all the errors that you get from using the floating point arithmetic on computers. But in addition to that, you get statistical errors. These errors due to the random sampling you make. And well, in this very simple example, it was a so-called static Monte Carlo. So the probability distribution you used for sampling didn't change. But the more advanced ones, they use Markov chains. And then what you will see is that this statistical error actually depends on the autocorrelation time of the Monte Carlo. It's a property of the method, yeah. So basically, if you go to the next slide and you see if we want to control the errors now, we can just assume that these computational errors, yeah, these rounding errors, the floating point errors, that they are smaller than the statistical errors. That is usually the case. So the statistical error needs to be controlled for. It needs to be improved. So we somehow need to control this autocorrelation time. Yeah? It's a direct property of this method. And the question is, how can we achieve this? And here again, on the next slide, I'll have Sokal, and he suggests something. I think also, if you are using this methods, that is something that is in the back of the minds of all the practitioners. This hierarchy, it's rarely made explicit, but so I think this lecture by Sokal is really great because it's an introductory lecture, and he makes these things explicit. So he suggests that there's the following hierarchy, specifically for Monte-Carlos here, that if you can prove that the Monte Carlo has a certain autocorrelation time, that is the best thing you can do. Yeah, then you have a mathematical guarantee of the error, basically. If you cannot do that, you have to resort to some kind of empirical estimates of that autocorrelation time, which basically means empirically estimating the error, and that is often done in some kind of post hoc fashion. So you let the thing run, and then you look at the the graph of the error going down, something going down, similar to what machine learning people do when they observe the training and the test error, and they just look at these graphs and see them going down, and yeah, at some point they are satisfied. And here actually it's the same. So this is like maybe a previous instance of exactly the same technique, and of course, because Monte Carlo is a statistical method, right? There can be fluctuations in that. So you can plot your autocorrelation time, and it will go down, but then it will fluctuate. It will go up a bit. It will go down a bit again. We would have seen that in my Monte Carlo example too already. But yeah, so there's no mathematical guarantee anymore if you do this empirically, right? So sometimes you have like maybe heuristic arguments, or you are convinced that your algorithm is well behaved enough that it won't do anything crazy in the long run, but there's no mathematical guarantee for that. So, and this is what Sokal suggests here, and I think we can generalize this hierarchy from Monte Carlos to all approximation methods. So this is on the next slide. Yeah, so I had these 2 points. So what we see is that proving is really hard to do. Yeah, I already said that. Normally it's for lots of Monte Carlos that are employed in practice. It's not done, and it's maybe not even possible. And the danger with with the empirical estimation is that it requires assumptions about the Monte Carlo. Yeah, some kind of inductive assumptions which are possibly incorrect. And yeah, so I will give like a generalization of this hierarchy of error control on the next slide now. Okay, so I think it's also very suggestive that we have this general hierarchy of error control in approximation or in computational methods, namely that if we can mathematically prove error bounds or something like that of our method, then this gives us absolute error control. Yeah, so we can turn the knob, and our error will go down, and it's mathematically guaranteed that it will do that. So I'll just call this theoretical error control for the time being. And the second element of this hierarchy, so the lower one, are these empirical estimates, and they only give error control relative to their assumptions, which I call practical error control. So basically, the amount of control you leverage on your error depends like really strongly on the assumptions you make to arrive at that empirical estimate. So in Monte Carlo, that would be autocorrelation times, but in other numerical methods, there are other assumptions you have to make to empirically estimate how that error will behave. Okay, we can go to the next. Yeah, and I think this also induces some kind of distinction between approximations. So we can distinguish here between ideal and real approximations. And I think ideal approximations are the one that actually have theoretical error control. Yeah, so these are the best approximations that we can hope for, and we would all be happy if we had them. Yeah, and in their case, this naive scaling, yeah, so the scaling the error scaling which only depends on the computing power, that actually holds. We are mathematically guaranteed that it holds. But unfortunately, the theoretical error control is rarely the case. So ideal approximations in practical scientific contexts are also rarely the case. What is much much more often the case is that we have real approximations which have only practical error control. And yeah, these real approximations, they are as good as their level of error control. But this also means that naive scaling doesn't hold, right? Because we can increase computing, but we have no guarantee that it will really reduce the error. So we might observe this in a certain, for a certain area in compute, but there might be things going wrong. And actually, things can go terribly wrong. Yeah, these Monte Carlo things, they can get stuck in so-called metastable regions where the error will be insanely huge. It will just give you no sensible results anymore. So you have to somehow make sure that this doesn't happen. But in the end, that this doesn't happen is only guaranteed by some kind of assumptions you make, which don't rely on your computing power. Okay. Next slide, please. So I will conclude this talk by pointing out the problem of hiding practical error control, right? So if theoretical error control is the case, we basically have no problem. We can hide these methods behind layers of APs, whatever, and we can let them loose on the end user, and they basically, it's hard to abuse them. But if we have only practical error control, it's a problem if this practical error control is hidden from plain view, and is often hidden from plain view, right? So if you consider the huge numerics packages, MATLAB, scientific Python, NumPy, even in Mathematica, you have some kind of easy to use interface to the numerical method, but to make it easy to use, all these assumptions that go into these numerical approximations, yeah, all the practical error control is hidden from the end user. It's also sometimes just hidden in recipes for implementation. Yeah, if you have if you want to implement a numerical approach yourself, you're probably not going to invent a whole new algorithm. You're going to, yeah, you will look in the book numerical recipes for C or whatever, and it will tell you, well, for solving a certain kind of differential equation, you maybe can use this type of Runge-Kutta, which has this type of optimization and will work good on this and this kind of problems. And then you forget about it, right? And then you just use it. So just using these things is always a bit dangerous, especially if it's hidden behind lots of layers, like in these very abstract, high-level constructs, like numerical Python, where users just assume that there's a kind of theoretical error control, but in truth, only practical error control is happening. So they think if we increase compute, it will get automatically better, but sometimes it doesn't. Yeah. Okay. So we can go to the last slide. So I'll just conclude by saying this naive view of error improvement, the naive scaling through compute, is often wrong, although it's suggested in contemporary literature all over the place. Then the problem is that we have practical error control, and practical error control is decoupled from compute. It doesn't depend on compute in general. This is why we cannot improve errors, or we cannot improve real approximation by just improving in compute. And I would even go so far and say that if practical error control is hidden, if it's hidden from the end user, and if it's just used, then there's no error control at all. Okay, so that's it.